When someone says a system is slow, that word covers two very different problems. Is each individual request taking too long? Or is the system struggling to keep up when many requests arrive at once? In this video, we will pull those two ideas apart, give them precise names, and show you exactly where to look when things go wrong. Here is a familiar story. You test your feature locally and it responds instantly. You ship it, traffic grows, and suddenly users are complaining about slowness. The problem is not that your code changed, it is that you were measuring the wrong thing, under the wrong conditions. Before you can fix a performance problem, you need precise language for what is actually happening. Picture a busy coffee shop. If you walk in alone, the barista is all yours and your wait is short. That wait time is latency. But now imagine 100 people arrive. Even if each drink still takes the same time to make, the shop can only serve so many per hour. That rate is throughput. A system architect has to think about both dimensions at the same time, because improving one does not automatically improve the other. Every request in a layered system passes through at least 3 tiers. The presentation tier adds network and protocol overhead. The business logic tier burns time on computation or on waiting for other services to reply. The data tier is almost always the most expensive stop. Disk reads, slow queries, and shared connection pools all live here. The total latency a user feels is the sum of all three. The throughput ceiling is set by whichever tier runs out of capacity first. That tier is called the bottleneck. Follow one request from the moment a user presses a button. First, it crosses the network to reach your presentation tier. That tier passes and routes it down to business logic, which may call external services before reaching the data tier. The query executes, and this is where most latency hides. Then the result travels all the way back up. Each hop adds time, and any hop that is slow or saturated becomes the bottleneck that caps your entire system's throughput. Latency and throughput improvements often pull in opposite directions. Caching dramatically lowers response time for individual requests, but now you have to reason about stale data. Asynchronous processing lets you handle a huge volume of work by queuing it, but any one job may wait longer before it is picked up. The architectural skill is knowing which pressure matters most for the feature you are building, and choosing the technique that addresses that pressure without introducing an unacceptable cost on the other side. The most common mistake is optimizing before measuring. Run load tests that simulate real concurrency, hundreds of simultaneous users, not one request at a time. Profiling will show you which tier is saturated. Only then should you reach for a technique, caching near the data tier for repeated reads, an async queue to move slow work off the critical path, or co-locating services to cut network round trips. Each technique targets a specific cost, so matching the tool to the measured problem is everything. To wrap up, latency and throughput are the two dimensions of performance, and confusing them leads to solving the wrong problem. Bottlenecks almost always hide in the slowest shared resource, usually the data tier. The right tool depends on which dimension is hurting. Caching and fewer hops lower latency, while async processing and horizontal scaling raise throughput. And none of this works without measuring under conditions that reflect real usage.